Today I will talk about the cone angle for PR3 ligands, and then I will talk about some complexes that includes the PR3 ligands. I show some examples for the complexes, and I will talk about the infrared stretches of CO, rate of the reactions, which is affected by the cone angle, and so on. But firstly, what is the cone angle? The cone angle is an important parameter used to describe the steric bulk of the phosphine ligands, and especially in organometallic chemistry, it gives a measure how much space a ligand occupies around the metal center. Cone angle has significant effect on the behavior and reactivity of metal ligand complexes. And we can draw the cone angle. I want to represent the cone angle. We have a metal center and we have a PR3 ligand. So one of the R group goes to back, one of them is coming to us, and one of them is on the surface, and we have the R groups. And simply this theta is our cone angle. The cone angle is important. For instance, for pH3, the cone angle is 87 degree, so it is pretty small. For PF3, which is a little bit bulkier than the pH3, and it is 104 cone angle, and this one POH3 has 107 cone angle, and it can be very high. For instance, if we go to this one, C6H53, cone angle becomes huge, and it is 145 degrees. And we can consider a reaction. For instance, if we have a nickel CO4, and how many PR3 can we add to this compound? And this is a very important question, since cone angle directly affects the number of edible phosphine ligands. If the ligand has a small cone angle, for instance, if it is a PPH, not PPH3, if it is pH3 for instance, then you can add all the ligands. This complex can be nickel pH3. However, if the cone angle is high, you might not add more than 2 PR groups. And there are some important points of the cone angles. Larger cone angles result in greater steric hindrance, which can prevent the coordination of multiple ligands, favor lower coordination numbers, influence the geometry of the complexes. So for instance, bulk ligands can dissociate easily. Cone angles affect the reaction rates and selectivity. Electron-rich bulky ligands may push more electron density to the metal, but also block substrate. We can make an example. So we have this complex, which is molybdenum CO4L2, and it reacts with the carbon monoxide. So we are leaving one of the ligands, and we are putting the CO here. So compare the rate of the reaction when ligand is this one and when ligand is PPH3. So firstly, there's a steric angles, and steric angles are different for these two ligands. Now for the first one, steric angle is 136 degrees, and for the second one, steric angle is 145 degrees. And the rate of the reaction for the first one is 1.3, and the other one it is 320. This is the rate of the reaction. So it is very high for the second one. The reason is that bulkier ligand leaves easily from the metal center. Because bulky ligands increase steric hindrance, which destabilize the complex, this facilitates the ligand dissociation, especially in a dissociative mechanism. There is also electronic effect for this reaction. So firstly we have p-methyl pH2 ligand, and it is more electron donating ligand than the PPH3 ligand. And PPH2 methyl increases metal ligand back bonding, which causes stronger molybdenum ligand bonds. Stronger molybdenum ligand bonds causes slower ligand dissociation. And compare the VCO stretching for the following complexes. We have two different complexes, and in the previous video I explained PF3 is a pi accepting ligand, and it is a weak sigma donor ligand. On the other hand, PPH3 is sigma donating ligand, and if we both look at the compounds, both are 18 electron complexes. So the only difference between them is these two ligands. And we have to know a few things. First, the CO bond strength is influenced by the metal to CO pi back bonding. More pi back bonding causes weaker CO bond and lower VCO. Less pi back bonding causes stronger CO bond and higher VCO. So for our example, VCO in nickel CO3 PF3 is bigger than the VCO in the nickel CO3 PPH3 complex. So this is a sigma donor ligand, and electron density on the nickel increases. When it increases, pi back donation increases and VCO decreases. So this is the explanation for our case. And the same thing can be done for this one. It is a pi accepting ligand, so electron density on the nickel center decreases, which decreases the pi back bonding for the CO molecule. When pi back bonding decreases, VCO also increases, since VCO bond becomes stronger if the pi back bonding decreases. So there is a reverse relationship between each other. I want to give another important point. For very bulky ligands, the metal ligand bond may be distorted, and this causes lower sigma donation, and it can affect the VCO stretches. But for our example, I think these are not very bulky ligands. So there are very bulky ligands like that I wrote in previous slides. For instance, this is a very bulky ligand, and metal ligand bond may be distorted if this ligand takes a role in this kind of reaction. And I want to make another example. Consider these two complexes. The only difference between them is the number of ligands. and compare the nickel carbon and nickel p bond lengths. So we need to consider the ligands. So firstly, CO is stronger pi acceptor than the PPH3, and adding a second PPH3 increases the pi back bonding. This makes metal C bond stronger, but CO bond weaker, which is not the part of this question, but I want to mention that. Due to steric effect in the biphosphine complex, there is a repulsion between bulky PPH ligands and nickel center is more electron-rich, which weakening the nickel p bond. So there is a steric effect on complex 2, and this is complex 2 for me. Okay, this is complex 2 and this is complex 1. And there is a repulsion between bulky PPH3 ligands in complex 2. So I want to make a table to explain the question more easily. Firstly, we have a nickel carbon bond and we have nickel p bond, and we have two different complexes. So nickel carbon bond is longer for this complex. The reason is that there is a less pi back bonding, and nickel p is shorter. The reason is that less steric hindrance. We have only one phosphine ligand, and in complex 2, this is the complex 2, we have shorter nickel carbon bonds. The reason is that there's a more pi back donation. This is more here. And nickel p bond longer. The reason is that we have two phosphine ligands, so there's a strong steric effect. And this is all for me today.